Now we want to look at some application problems that we can do now that we've learned about angles. And so these talk about the difference between linear and angular speed. Now linear speed is kind of what you're used to most of the time. So for example, if you're driving your car down a road, what your speedometer shows is your linear speed, kind of how fast you're going in a linear manner. Now, if something is rotating around, think about a Ferris wheel or a wheel rolling, then we can also talk about its angular speed. And that, if you think about a point on your circumference, how fast it's going kind of through all the angles, okay, how fast that is rotating. So this says, if a point in motion on a circle of radius r through an angle of theta radians in time t, then linear speed and angular speed are given by the following formulas. So our linear speed is r times theta over t. So your radius of how big your circle is, theta, now it's really important to note that theta must be in radians. Okay, so whenever we're dealing with angles here, we're going to put them in radians. And then we have a time. Now, another way to write that is the linear speed is the radius times omega. And omega, this little w thing, is actually the angular speed. And to get the angular speed, we take the angle divided by the time. Okay, now if you want to know the arc length, how far something has gone around the circle, and when you're talking about a wheel moving, that'll be how far the wheel has actually gone. We use an S, and the formula is the radius of the circle times how many angles you've gone through. Okay, so let's go through a couple of problems just to kind of get the feel of this. So the first one says, if a radius of a wheel rolling on the ground is 80 centimeters, if the wheel rotates through an angle of 60 degrees, how many centimeters does it move? So what this is asking us for is actually the arc length, or how far it's going. And it says to round our answer to 2 decimal places. So we want S. So this formula we want to deal with is S equals R theta. Now we're given our radius, 80 centimeters. Now we need theta, and we're given an angle of 60 degrees, but that's in degrees, and I reminded you that theta needs to be in radians. So we're going to take 60 degrees and convert it into radians by multiplying by pi over 180 degrees. And if in your calculator you take 60 divided by 180 and turn it into a fraction, you see that it's 1/3. So 60 degrees is the same as pi over 3 radians. So we're going to multiply this by pi over 3. And this is another case where we need our calculator. So we're going to take 80 times pi, so your pi is above the little caret button in yellow, divided by 3. So we see that this is approximately 83.78 centimeters. Okay, so we basically, what we're saying is this wheel has moved about a sixth of a turn, and it would have moved forward 83.78 centimeters. Okay, so number 2 says the Ferris wheel has a radius of 25 feet. The wheel is rotating 2 revolutions per minute. Find the linear speed in feet per minute of a seat on the Ferris wheel. Okay, so again, here we're going to have to be very careful about what we're given and all the units and everything like that. So, here we're told that the radius is 25 feet. And what we want is the linear speed. Which we give a v for velocity. And this is going to be r theta over t. Now, we have the r, and we actually have the theta over t by talking about 2 revolutions per minute. Now, if we think about 1 time around the circle, that's 2 pi radians. So if we've gone around twice, times 2, that's going to be 4 pi. So our theta would be 4 pi over 1 minute. So we'd have 100 pi per minute, and let's see, this is about 314.16 feet per minute. Okay, so if you're given RPMs, revolutions per minute, you can figure out your angular speed knowing that one revolution would be 2 pi radians. So let's go ahead and do one more problem. So it says the minute hand of a clock is 6 inches long and moves from 12 o'clock to 4 o'clock. How far does the tip of the minute hand move? Give your answer in inches and round to 2 decimal places. Okay, so we got to think of a clock. And we're told it's going from 12 to 4, so it's going like this. And we want to know how far it moves, so that's going to be its arc length. We need S equals R times theta. So we know that our R is 6 inches, and we need to know kind of how far this has gone. Well, if we think, for a clock we've got 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and they're equally spaced. Okay, so if the whole thing was 2 pi, and we've divided it into 12 spots, between each kind of number, each hour would be pi over 6. Well, we've gone 4 of them, so we want pi over 6 times 4, or 4 pi over 6. So that's going to be our angle. This angle between 12 o'clock and 4 o'clock would be 4 pi over 6. So to find our arc length, we're going to take 6 times 4 pi over 6, which would give us 4 pi. So we'd see that the tip of that minute hand has gone 12.57 inches.